cross-sectional volume. I found this GeoGebra visualization that somebody made, and it is really, really nice for you guys to be able to look at. So with cross-sectional volume, we're doing a little bit more than, well, we're doing something different than rotational volume. However, if you can imagine, no. Good, do that. Yes, there we go. If you could imagine these being full circles instead of semicircles, then in a way, rotational volume is just a type of cross-sectional volume. But the thing is, with rotational volume, it's always an axis of rotation that's either on the edge of the region or completely outside of the region. And so in that way, it's different. But with cross-sectional volume, at least for today, you are just going to be dealing with particular shapes. And here's what I want you to try to imagine. So I'm circling the XY plane right here. Imagine you have a bread pan that has this shape to it. So you're creating this really fashionable cake or bread slices, whatever. And so the base of the region, the base of the cooking region looks like this across here. Now, when you take the cake out of the pan and you like put it down on the breadboard and you see this that I'm encircling being on the breadboard itself. Imagine that the breadboard is the XY plane. Now, you're going to imagine maybe that your keyboard or whatever is the breadboard. And you're looking down on that breadboard and you've got a knife ready to make bread slices or cake slices, whatever. Now, you are going to be told that these cross sections are either perpendicular to the x-axis or perpendicular to the y-axis. So from the visual point of view that you are used to, if it says perpendicular to the x-axis, that means you're taking a knife, and if you can see what I'm doing, I'm going slice. Perpendicular to the x-axis. But in order to cut out a full slice of bread, you make two cuts, and then you can pull out one slice of that bread or cake. Now, you can make thin slices. You can make thick slices. The thickness of that slice of bread is your differential. It is your delta X or your delta Y. If you are making cuts perpendicular to the x-axis, then that means you are making these long vertical slices. What is your differential? What is that width of your bread? Is it change in X or is it change in Y? If you're making these vertical slices, yep, it's dx. So anytime the cross sections are perpendicular to the x-axis, dx is your differential. If they say perpendicular to the y-axis, then you are awkwardly trying to make slices and hoping you don't accidentally cut yourself. You're kind of going, That's a time where I have to be very, very, very careful with not cutting myself. Anyway, now you are given a particular shape. At least that's what we're focused on today. Later, we're going to add on to cross sections and look at bigger pictures of it. But for today, this is like the standard type of textbook problem But your textbook, it presents them in such a weird way that I found it's better if I just rewrite stuff. So I have a worksheet, and I've got the answers posted as well. But this is what it looks like if you are working with squares. And what's cool with this, oh, that's right, I can do this. I can fit it to screen. There we go. So over here on the left is the XY plane. And that's what you're going to be focused on as you're setting up your integral. Over here is a three-dimensional view. You want to realize that the gray plane that you see is the XY plane that you see over here, just positioned in a three-dimensional way. Then whatever shape the cross sections are, they are perpendicular to the XY plane, which actually at that point we start using the word orthogonal, but orthogonal is perpendicular. So they are, I want you to see the visual nature of what is being described. And what's cool is you can play with this and you can make the number become more. And then you can look at moving it along the entire curve, creating more, creating less, to get an idea of what this is doing. Then we also have an example of equilateral triangles. That's another shape that they like to do. And then there's also some semicircles on here. But the way this is made, I at least don't know how to change the functions that are involved. I have another one that you can look at where you can change the functions. But let me make sure to clarify also. When you're looking at this three-dimensional picture, they are designating blue versus red curve for blue versus red curve. That means this red axis is the x-axis and this green axis is the y-axis. And then you might be able to see a little bit better how these thicknesses, do you see where my arrow is? And I'm trying to show the thickness of that slice is a horizontal cut. All right. The other one that I found, is it this one? Oh my gosh, lag time is just ridiculous right now for me. Da, 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 da. Well, maybe I'll just leave you some links. And I'm not going to sit here and wait for my internet to get GeoGebra loaded. So anyway, that was that. Now, you need to be familiar with certain area formulas. So I'm going to take you through finding area formulas. Now, when I give you a quiz on cross-sectional volume, you need to know these area formulas. When the test for this chapter comes out, you need to know these formulas. When the AP test comes around, you really should know these formulas, but you can come up with them. Just realize it's going to take time. Some people can come up with formulas so quickly that it's not even a time issue. So, you know, I used the letter S for side last period, and I'm thinking I don't want to use S again because it looks too much like a 5. So, I want to stay away from using the X variable. How about I use the letter A? No, B. I'll use B. It doesn't really matter, actually. So, if you know the length of one side of an equilateral triangle, you most likely aren't aware of the actual area formula to just spit it out. But I'm going to show you how to come up with it. And then you can decide if you want to come up with it on your own at times as well, but it does take time. So here's what we're going to do. Are you ready? In this equilateral triangle, I am going to draw the altitude. Ding. Okay, that wasn't quite perpendicular. I should try again. That was sad. Very sad. Better. Okay. Now, with this being an equilateral triangle, do you agree that this slices the triangle into two congruent triangles? You actually know these triangles. I want you to take a look and tell me more than just they are right triangles. Tell me beyond they are right triangles what these are. Oh, nice. That was quick. That was very quick. I didn't expect it to come that quickly. So you want to know that the equilateral triangles, well, you remember that they're all 60-degree angles, right? And if you are making an altitude in an equilateral triangle, you're cutting this angle in half and getting 30-degree angles. Now, B is the length of a hypotenuse of one of these 30, 60, 90 triangles. And actually, through the equilateral triangle, you can see a lot better why the length across from 30 is half the hypotenuse. Now, in order to find an area formula, I need to know the altitude. Now, either you remember how to find the altitude based on special right triangles, or you can Pythagorean theorem your way to that formula if you forget it, which means the length of the altitude squared plus half of b squared is equal to b squared. And hopefully you can see what am I trying to do? What am I trying to do? Oh yeah, square root. And subtraction. Oh, don't take the square root yet, silly. Now, do you remember that to go from the length of the side across from 30 to the length of the side across from 60, you multiply this length across 30 by root 3. That creates this number. So now, what is the area formula of an equilateral triangle? So root 3 over 4 times the length of one of those sides squared. The other type of triangle that you might be asked to use as a cross section is an isosceles right triangle. But if you are given an isosceles right triangle, you have to know whether the side that's sitting on your xy plane, you need to know if that's the hypotenuse or one of the two legs. Now, isosceles right triangle. Isosceles right triangle. Is that anything special? Oh, you're too quick. So right triangle, if it's isosceles, it has to be the legs that are congruent. And in a right triangle, if the two legs are congruent, the angles that are not the right angle have to be equal, and those have to add up to 90. So these are 45, 45, 90 triangles. So now we want an area formula first based on if I know the hypotenuse. Do you remember how to go from the length of the hypotenuse to the length of a leg on a 45, 45, 90? And if you forget, here's what you can do. You can say, all right, what if these are both length A? Yep. If you don't know the formula, you do know Pythagorean theorem. And then you can just go, all right, a squared plus a squared equals h squared. La 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 la. La 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 la. Ooh, look at that. Oh, silly me. Deep. Now does it come back to you? To go from hypotenuse to leg, you divide by root 2. So if you know that these legs are h divided by root 2, what is the area? And area is always 1/2 multiplied by 2 perpendicular dimensions. And then if I simplify that formula, it's a number times h squared. What number is it? Yep. The next one's almost too easy. If you know the length of the legs, what is the area formula? And I decided to do like a cursive L for leg. The other area formula that it helps to be familiar with, but you really don't have to memorize this one as much, is the area of a semicircle, but based on its diameter. So when you look at this area formula, you should start off with knowing if it's a semicircle, then it's half the area of a circle, which you know to be pi r squared. What is the radius in terms of the diameter? Mm-hmm. So if you want, you can just throw this formula out on the plate. You've got to make sure that this diameter, that's going to be like your top y minus your bottom y, has to be divided by 2 and then squared. Or you can remember a simplified version of this. Another formula would be the diameter squared times what number? Pi over 8. Now, you don't need to memorize this formula. It's a convenience, but you know enough about areas of circles that you should be able to at least take it from here. It's just a matter of how good of a memorizer are you. So as far as other shapes go, if you get a square, you know that formula. If you get a rectangle, they have to explain to you somehow either how the two dimensions are related to each other or give you information about how to find the other dimension. Your focus is always on an area formula, though. So I've got a couple of examples where I'm just going to, I'm only going to create 2 regions to save us some time, but look at using the various formulas and have you see that it's really not that different to come up with an integral based on the different shapes, as long as you know the area formulas. So know that you have to be told whether the region or whether your cross sections are perpendicular to the x-axis or perpendicular to the y-axis. So while this is problem number 1, number 2 is going to be perpendicular to y. You need to be ready to deal with this either with or without a calculator. So let's graph the region on the xy plane. Yeah, good enough. So you should see that this is the region in between the two functions. Now, if your cross sections are perpendicular to the x-axis, then you're going to draw segments only in the region that are perpendicular to the x-axis. When we do rotational volume, the radii often come out of the region because they have to attach to an axis of rotation. These don't have an axis of rotation. There's just an area formula for each planar slice of this solid. And you're basing everything on the area formula of a planar slice by a plane slice through the solid. And if you are perpendicular to the x-axis, what is your differential? Mm-hmm. You have a teensy tiny little horizontal cut to take it from being just a square to a rectangular prism. So, first thing, Realize you're using the differential dx because you are perpendicular to the x-axis. That means you need the x coordinates of intersection points, A and B. To find those intersection x values, set the two functions equal, solve that equation. Then, once the differential is down and you've got your AB, what is the area formula? For part A, it's a square. So area formula of a square. Length of side squared. Then the length of each side is based on which x you are located at. And for the x you're located at, the formula for the length of this side is the top y minus the bottom y. In this problem, the top y value is x plus 1 minus the bottom y value is x squared minus 1. At that point, your integral is set up, and it's a matter of solving that integral. And I'm not going to go through the integral solving because I want to make sure that you guys have a good amount of time for your quiz today, which is on just area. And I'll set you up for it. Make sure you're ready. Okay, so that's the answer to part A. Now, how different is part B going to be from part A? If you are doing equilateral triangles instead of squares, you are still perpendicular to the x-axis. You're still using this region. What is the area formula of an equilateral triangle based on the length of a side? Root 3 over 4 times length of side squared. And then, what is the length of the side? You already found it. Top y minus bottom y for that same region. You know, I just thought about it, but I find it kind of crazy. Last year's AP exam, everything we're doing right now wasn't on the AB exam. Do you guys remember how they cut like a huge chunk of topics? It was not. All of this area volume was not on their AB exam. It bothers me to no end. Pretty much everything you've done so far was on last year's AB exam. It was ridiculous. I'm still unhappy. Okay. Then lastly, semicircles with diameter on the base region. So you've got choices. Either you use the formula pi over 8 times diameter squared, or you use the formula, you name it, pi over 2, but the radius is half the diameter. So again, you can either write it this way or this way. And if you see how that divided by 2 squared comes together with the 1/2 to make an 8, it's actually a lot easier to write it this way. So that was cross sections perpendicular to the x-axis. Number 2, cross sections perpendicular to the y-axis. Let's draw these graphs. Oh, that's way too steep. What am I doing? I'll never get them to meet if I use that steep. So I've got the region between the two curves, but this time cross sections are perpendicular to the y-axis. So that means in the region, draw a little line segment that goes from one function to the other that is perpendicular to the y-axis. That means any integral that I set up for these cross-sectional volumes, are they using differential dx or differential dy? Dy. That means I need to make sure that I find the y coordinates of intersection. I can see that 0 is one of them. And then I'm going to real quickly just solve when x is 2, the y coordinate that goes with it is 4. So I need to set up my integral to go from y equals 0 to y equals 4. So now I've got a bit going. The next step is area formula. The first one is rectangles, and it's telling you that the height is twice the length of the width along the base region. So what it's saying is this is the width of a rectangle, and that rectangle is coming up off the screen perpendicular to the plane that that screen exists on. I used to say whiteboard, but oh my goodness. So I'm trying to draw a little tiny dy going with it, but I think I'm just going to take that off. It's too thick. I'm not drawing to scale, but if W is this width along here, then the height is 2 times W. And what does that make the area formula? 2 times that width squared. And remember that these equations do not get written down until the whole integral is almost done. Actually writing these functions into your integrand is the last thing you should be doing. And then you want to look carefully. You need the right x-coordinate minus the left x-coordinate and x-coordinate. So for y equals x squared, that gives me root y equals x. Technically, it gives me plus or minus, but we are using the right half where x is a positive number. We aren't using the left half where x is a negative number over here. And then the left x-coordinate is coming from the line y equals 2x. And so the right or the left x-coordinate is y over 2. And at that point, you have an answer for an integral that will find that and then go about integrating. The homework that you have today, there's some more obvious way to figure out. You mean to figure out which is left, which is right, kind of thing? Yeah. More rigorous way. You could draw a horizontal line. And if you draw in the order that you normally draw graphs in, you'll draw left to right. And if you do that, you're hitting the smaller thing that needs to be subtracted first, then the larger one who gets to lead the subtraction. So if we're really bad at uh-huh. Mm-hmm. Uh-huh. If you can't graph it to see it visually, you have to at least know where the region exists between. It's hard to be able to come up with a way without seeing its graph, because there are going to be some places where one function is further to the right than the other, and they might cross each other and swap. I guess the good news for you is usually on the AP test, they draw the picture. Okay. I was holding back on saying that, but. Mm-hmm. They won't give us one where it's like hard to figure out. Like, no. There's no other way to go, like method we need to know how to figure out it. Frankly, I'm disappointed in the AP test and the fact that they don't expect you to really graph much without a calculator. I'm personally disappointed. You're probably not. As a math teacher, I'm like, come on, people. But usually either it's in a calculator section, and they often draw the picture even in the calculator section where you could draw the picture in your calculator. Every once in a while, they don't. Every once in a while, you have a problem that shows up in a no calculator section, and you have to figure everything out. They don't tend to go beyond polynomials or functions that are fairly quick graphs that you should know. So what I would say is I can't guarantee you that the AP test won't ask you to graph a function on your own. It doesn't happen that much. And while you're testing from home, I have to also be aware that you guys have the ability to graph things without me knowing whether you have used a graph or not, if that makes sense. That's one thing that teachers are very leery of with you guys taking these tests from home. And that's why so many of us were just, our jaws dropped when they said last year, students will take their AP tests at home. What? What? I'm sorry if I screeched into your ear, but oh my gosh. I'm still just like, okay. Anyway, I'm going to move on with my life. So, here we are. And I've got a couple more problems, and I want to be careful because I want to get that quiz started for you so you have enough time. So at this point, you probably realize that if I'm still using the same region and I'm still perpendicular to the y-axis, then B and C are going to start off with the same limits and differential. The only difference is the area formula. If you have a right triangle with the hypotenuse on the base, then the area formula is 1/4 times the length of the side squared. If it's isosceles right triangle with leg on the base, then it's 1/2 length of side squared. And the length of the side continues to be the right x minus the left x. And then from there, you can use your calculator or integrate by hand. I want to point out to you the homework problems, and this is videotaped, so if you need to write this down, it'll show you in just a moment, or you can look at that. For your homework assignment, for 1 and 2, you are using a graphing calculator. That means you're going to find the intersection points with your calculator, you're going to solve the integrals with your calculator, all of that. For 3, 4, and 5, you are not going to use a calculator. And I present this to you with the understanding that when you take that AP test, it is probably going to not be from home. Now, I want to point out to you that I want you to solve by hand the integrals that you get for 3 and 4a. But for 4b and number 5, you're going to only do setting up the integral and stop. With setting up the integral, you do have to find the limits of the integral. You need those numerical limits of the integral and basically have an integral written down all ready to be integrated, but you just don't integrate it. And the reason being is those are hideous problems to integrate by hand. Seriously hideous. So I just want to clarify that for you. Now, for the quiz, if you do not have a graphing calculator, some of you don't have graphing calculators. So you have Desmos. So I want you to listen real quick and I will explain to you how you can do everything with your calculator. I mean with Desmos, as well as your calculator. By the way, if you have a graphing calculator, you really should use it because you've got to get used to it for the AP exam. If the AP exam is not something you plan on taking, I know. Okay, let me put it to you this way. If you are not signed up to take the AP exam, use Desmos. Because we're still going to be in a somewhat quarantine situation when I give you the final anyway. But if you are prepping for the AP exam, you want to be used to that calculator. You're not going to have a Desmos option. So with Desmos, you can name the function and you can solve a definite integral. Now, what I'm going to do is I'm going to show you that you can literally just type whatever letter you want of x. You can even use the keyboard. You don't have to. Equals, and I'm going to throw in another function, just x, just to show it. Now, if you're using Desmos, you are able to hover and see the intersection points. And if you're hovering and you don't see them, like this, you need to click on something and eventually you'll be like, oh, there they are. And you can just hover and see them. For the integral, if you open the keypad up, you have under functions, miscellaneous. And right here at the bottom left corner is the integral. Now, if I want to find the area between the two graphs of these functions, the first intersection was 0. Then I can click over here. The other one was pi over 2, and there's a nice little pi button, but you can also type in the letters pi and it will make a pi. And then name f of x, whoops, minus g of x, and then dx. And, oh, you know what I just realized? Yeah, I put the subtraction order incorrectly. Now, if you're on an AP exam and you realize you put the subtraction order incorrectly in your calculator, you know what you do? On paper, you make sure it's written correctly, but then you just change the sign. Don't sit there and redo it. I'm going to redo it just for the sake of being correct with what I'm showing you. But there you go. You can use Desmos that way. All right. And it just gives you the answer right there. No push enter, just done. You know, I'm actually a little bit curious if I don't put the, yeah, you have to have a parentheses around your integrand before the differential to get that number to pop out. All right. I'm going to call it a day, and then I'm going to open